Yeah, okay. Um, Very good afternoon to all. Welcome to another session on mobile communication networks. Today we are going to start unit number 3. The title of unit number 3 is Antennas for Mobile Terminals. Okay. So we are going to design an antenna which are used in mobile systems, mobile telephones or mobile users, how they are being configured. Okay. And how this antenna is designed at base station level. Base station is what we had seen unit number 1, BSC. Base station will be there, which will get the signals from the transmitting users. It will acquire signals. So depending upon the availability of the channels, it will access. And if the receiving user is free, it will send the signals. So how this base station antenna is being designed and its corresponding types, characteristics, which we are going to see in this unit. So before the antennas that are being used for mobile terminals, we'll be seeing the capacity of channels. So in unit 2, we had discussed about flat fading channel and frequency selective fading channel, slow fading and fast fading. So in that, we are going to take the flat fading and frequency selective fading. How much capacity can this channel accommodate signals for its transmission? Its characteristics, its equations, its efficiency, we are going to see. Then we'll be seeing the antennas and the different types of antennas, the configuration of antenna, how they are being used in base stations and in mobile switching centers. And we'll be seeing a specific PIFA, planar inverted field antenna, as a specific case used in mobile communication. Okay, so let us start today's first topic, which is capacity of flat fading. Antennas for mobile terminals, part 1. Okay. So let us see in part 1 what we are going to see. In part 1, we are going to see the capacity of wireless channels. So the first we'll be seeing AWGN channel capacity, which is additive white Gaussian noise channel capacity, resources for the AWGN channel, then CT AWGN channel, power and bandwidth manipulation for resources. Then the linear time invariant Gaussian channels, single input, multiple output channel, which is SIMO, single antenna In an antenna, single input and multiple outputs. In an antenna, multiple input, single output channel. So all this comes under your flat fading. And next we'll be seeing the frequency selective fading channel and a specific water filling power allocation scheme. Water filling mechanism we call it as. So let us start with the capacity of wireless channels. Why this capacity is to be determined is what we are going to see in this slide. So the growing demand for wireless communications makes it more important to determine the capacity limits of the underlying channels for the systems. The capacity limits the maximum data rate that can be transmitted over a wireless channel, considering a small probability of errors. So the information theory was invented by Claude Shannon, which we which would have studied it as Shannon's theorem, as a simplified. So Shannon is different, Fanon is different. So the information theory was invented by Claude Shannon in 1948 to characterize the limits of reliable communication. So his ideas were quite revolutionary at that time. The high data rates that he predicted were for telephone channels, landline usages, and his notation that coding would reduce error probability without reducing data rate or causing bandwidth expansion. So without expanding the existing spectral bandwidth and without reducing the data rate, he had postulated that errors can be reduced. Probability of error obtained at the receiver can be reduced was his prediction. So in some time, sophisticated modulation and coding technology validated Shannon's theory and so on. Telephone lines today. So we achieved data rates very close to Shannon capacity with very low probability of error. So Shannon's theory was postulated. He did not do much evaluation on that. So the recent studies and researchers were able to achieve his prediction. So in this topic, we'll examine the capacity of a single user wireless channel having a transmitter and receiver with single antennas. This is what we are consider. The only way to achieve a reliable communication over a noisy channel is to make error probability as small as possible. So if you reduce the error probability, more reliable communication will occur. So Shannon showed the surprising result that by more intelligent coding of the information, one can in fact communicate at a strictly positive rate, but at the same time with as small as error probability as desired. With a desired error probability of minimal, he has uh, shown us that coding can reduce errors. So this is why every coding theory requires information about information channel and information theory. So if there is a maximal rate, then the capacity of the channel for which it was being done would be appropriate. If one attempts to communicate at rates above the channel capacity, then it is impossible to drive the error probability to zero. So if one wants to uh, transmit a signal or transmit the information above the channel capacity, then he may lead to or he may get errors. means that the error probability cannot become zero. So whatever the information that he wants to transmit should be within the Shannon's coding theorem or Shannon's capacity theorem. So in this section, we'll be focusing on the additive white Gaussian noise channel, which is considered as Y of m is equal to X of m plus W of m. X of m is your input, Y of m is your output, and W of m is your weight of the noise that is being added independent over time. So this is a building block of all the wireless channels. It serves as a motivating example of what capacity means. The capacity of the time invariant additive white Gaussian noise channel and capacity of time varying flat fading channel is given in this presentation. So for a different channel information assumptions, there are different definitions of channel capacity depending on whether capacity characterizes the maximum rate averaged over fading states or the maximum constant rate that can be maintained in all fading states. Considering the flat fading channel capacity, the fading distribution is known at the transmitter and receiver. Meaning is that the receiver and the transmitter will know whether this channel is a flat fading channel or a frequency fading channel. So here we are considering it as a flat fading. The capacity under this assumption is typically difficult to determine and is only known in few special cases. So next consider the channel fade level that is known at the receiver, which is through receiver estimation, or when the channel fade is known at both the transmitter and receiver, which is receiver estimation and transmitter feedback. It is done during that. The fading channel capacity with channel fade level information at both the transmitter and receiver is achieved when transmitter adapts its power, data rate, and coding scheme to the channel variation. The optimal power allocation in this The optimal power allocation in this scheme for a frequency selective fading channel is a water filling, where power and data rate are increased when channel conditions are favorable, and it is decreased when channel conditions are not favorable. So next is the additive white Gaussian noise channel capacity. So here reliable communication is taken at a rate of R bits per symbols, means that one can design codes at that rate with arbitrarily small error probability. In order to achieve a reliable communication, one must code over a long block, which is to exploit the law of large numbers to average the randomness of the noise. So for this specifically, repetition coding can be used over long block that can achieve reliable communication. But the corresponding data rate goes to zero with increasing block length. So the repetition coding does not pack the code words in the available degrees of freedom in an efficient manner. So one can always pack a number of code words which is exponential in block length and can still communicate when reliably. So this means that the data rate can be strictly positive even as reliability is increased. by increasing the block length. So the maximum data rate at which reliable communication is possible is called as the capacity of the channel. So this is the terminology. The maximum data rate at which reliable communication is possible is called the capacity of the channel. So the capacity of the additive white Gaussian noise channel with power P and noise variance sigma square is given as C of AWGN is equal to half logarithmic 1 plus P divided by sigma square. This is for additive white Gaussian noise channel. Keep in remembrance. Capacity of the additive white Gaussian noise channel is equal to half 1 by 2 log of 1 plus P divided by sigma square. So next topic is the resources of AWGN channel. How does this AWGN channel or the additive white Gaussian lines channel behaves in a continuous time process? Okay. So first we'll define this additive white Gaussian noise channel. So this additive white Gaussian noise channel is being formulated for a flat fading channel that depends upon what is known about the time varying channel at the transmitter and or at the receiver. So for different channel information, assumptions or different definitions of channel capacity are being given depending on whether the capacity characterizes the maximum rate which has been taken as an average over all fading states of, or the maximum constant rate that can be maintained in all fading states with or without the consideration of probability of outage. So first we will consider the flat fading which we are seeing here now. So the flat fading channel capacity where only the fading distribution is known at the transmitter and receiver. So this is the case. So the capacity under this assumption is typically difficult to determine. It is known only in some special cases, which is a conclusion of this AWGN channel. Then the fading channel capacity with the channel fade level, where the information at both the transmitter and receiver is achieved or is known. When this transmitter adapts the power data rate coding scheme to the channel variations. So, considering the capacity in the AWGN channel, we will have a relationship y of m is equal to x of m plus w of m. So where y of m is your received, x of m is your transmitter, and w of m is your noise being added. So assume a channel bandwidth of b, okay, not b, w here, channel bandwidth w, and the received power as p. So we get the channel bandwidth as w log of 1 plus p n naught of w bits per second, which can be written as c capacity of the additive white Gaussian noise channel is equal to log of 1 plus signal to noise ratio 1 plus SNR bits per seconds per hertz. So this is obtained by the Shannon's coding theorem that proves that code exists that touches data rates arbitrarily close to capacity with arbitrarily small probability of bit error. So the converse theorem shows that any code with a rate that is greater than the channel capacity will have a probability moving away from zero. So for a discrete memoryless channel, which we had seen in information theory, the time invariant channel with random input x and random output y, the channel's mutual information is defined as I of x comma y summation x belonging to x, y belonging to y, p of x comma y log of p of x comma y divided by p of x into p of y. So where we get maximum achievable spectral efficiency. So for the additive white Gaussian noise channel, the equation of the information channel becomes an integral over continuous alphabets, and therefore it maximizes the input distributions in the Gaussian that results in a channel capacity. So for channels with memory, there are some channels will be there with memory. So for them, mutual information and channel capacity are defined relative to the input power and output sequences. So these are based upon the proofs of the Shannon capacity or the Shannon coding theorem, where Shannon capacity is generally used as an upper bound on the data rates that can be achieved under real system constraints. So at that time, the Shannon developed this theory of information that data rates over standard telephone lines were in the order of 100 bits per second. 100 bits per second. So then it was believed that Shannon capacity could predict a speed of roughly around 30 kilobits per second over the same telephone lines, which were not used in real. However, due to the breakthrough in the hardware modulation and coding techniques, these have brought commercial modems of today's usage, which are very close to the speed of Shannon's prediction, which was done in 1940s. In fact, modems that we are using nowadays can exceed the 30 kilobits per second limit on some telephone channels. So next is what we are going to calculate is the power and bandwidth manipulation of an additive white Gaussian noise channel. So the basic resources for the additive white Gaussian noise channel are the received power and the bandwidth. So which is log of 1 plus SNR. If this SNR value is high, the capacity increases logarithmically with P. If it is low, it increases linearly with P. Okay, in the sense, if the capacity increases logarithmically with P, every 3 decibel increase in the power yields only one additional bit per dimension. And if the signal to noise ratio is low, the capacity increases linearly with the received power P. So for every 3 dB increase, the power doubles the capacity. Keep in mind. So we should have the signal to noise ratio to be as lower. Then only the capacity of the channel can be doubled for every 3 decibel increase in power. So log to the base of 1 plus x is equal to x log to the base 2 of exponential when x is approximately 0, and if it is 1, it is log to the base 2 of x. So this is how do we calculate power. So received power is P, the signal to noise ratio SNR per unit dimension decreases the bandwidth as the energy is spread more thinly across the degrees of freedom. So in fact, it can be directly calculated that the capacity is increasing concave of the bandwidth W. So if the bandwidth is smaller, the SNR per degree of freedom is high, and then the capacity is insensitive to small changes in signal to noise ratio. So if the bandwidth is larger, such that the signal to noise ratio per degree of freedom is small, the capacity would be proportional to the total received power across the entire band, and it is sensitive to the bandwidth, and increasing the bandwidth will have a small impact on its capacity. So the formula for finding this bandwidth is W log of 1 plus P divided by N naught W, which is approximately given as W P divided by N naught W to the log to the base 2 of E. So which is approximated as P divided by N naught log to the base 2 E. So the capacity would be now linear in the received power, and increasing power will have a significant effect. So this effect is called as power limited regime. So this is the spectral efficiency of the additive white Gaussian noise in flat fading. So log to the base of 1 plus SNR versus the signal to noise ratio. If the signal to noise ratio is 20, the spectral efficiency will be around 3.8. Can. If it is 40, it is nearly 4.9. If it is 60, I get 60% of efficiency. It is that the resources is around 5.4. For 100% of efficiency, the require it is around 6.5. So next is the capacity of infinite bandwidth limit. The capacity of the additive white Gaussian noise channel with only a power constraint with no limitation on bandwidth is seeing that even if there is no bandwidth constraint, the capacity is finite. So for infinite bandwidth, the capacity will always be same as that of finite. So capacity of the additive white Gaussian noise channel for an infinite bandwidth will be equal to P divided by N naught or to the base 2 of E bits per second. So next we'll be determining the bandwidth versus the capacity as a function of bandwidth. Okay, capacity bandwidth measured in megahertz and the capacity measured in MBBS, megabits per seconds. So this dashed line represents the capacity and dotted line represents the limit for bandwidth tending to infinity, which is P divided by N naught log to the base 2 of E, which is around 1.42. Yeah. So the capacity will vary like this, which is a band limited range. So any doubts or any queries? Till the resources of AWGN channel, you can type in chat box. From 5 to 10 minutes of time will be given. Then we'll proceed on to the linear time invariant. Okay, since there are no queries, I proceed on to the next topic, which is linear time invariant Gaussian channels. Here the channels are time invariant, that is, the channel information is known both to the transmitter and the receiver, and they form a bridge to the fading channels. So the different types of channels in the linear time invariant Gaussian noise channels are the single input multiple output, SIMO we call in short. So it means one transmitting antenna and many receiving antennas, or multiple receiving antennas. So here we considered there are one transmitting antenna, and there is L receiving antennas. So here we'll be getting then the equation as y1 of m is equal to h1 of x of m plus w1 of m, where it varies from 1 to L. So here HL is a fixed complex channel gain from the transmitting antenna to the Lth receiving antenna, and WL of M is the additive Gaussian noise depending upon the antennas. So for deduction from X of M to Y of M, Y of M will be equal to Y1 of M, Y2 of M, Y3 of M till YL of M, the whole power T. So Y of M will be equal to H into Y of M, which is absolute value of H k square into Xm plus H into W of M. So where H is H1, H2, H3, H4 till HL, the whole transfer of M, W2 of M, W3 of M, WL of M, the whole transfer. So this is an additive white Gaussian noise channels ith received signal to noise ratio, which is uh, C. Channel capacity C is equal to log of 1 plus P of H square divided by N naught. So where P is the average energy per transmitted bit. So for multiple receiving antennas, there would be an increase in the effective signal to noise ratio, and they provide a power gain. So for L, which is equal to 2, if there are two receiving antennas, then we can write a H1 would be equal to H2, which is equal to 1 always. So then the dual receive antennas will provide a 3 decibel power over a single antenna system. Next is the multiple input, single output. So there are L transmitting antennas and a single receiving antenna, so which would be a reverse of the single input and multiple output. The L transmit antennas, which is multiple input, and a single receive antenna, which is your single output. So Y of M will be equal to H of into X of M plus W of M. So where H would be H1, H2, H3 till HL, the whole transpose, and the HT, and the H is the fixed channel gain of the transmit antenna to the receive antenna. So there will be a total power constraint of P across this transmit antennas, which is capacity is equal to log of 1 plus P of H squared divided by N naught bits per second per hertz. The transmission strategy maximizes the received signal to noise ratio by having the signals from various transmit antennas adding up in phase coherently and by allocating more power to the transmit antenna with better gain. So this strategy that aligns the transmit signal in the direction of the transmit antenna array pattern is called as transmit beamforming. The strategy where the alignment of the transmitting signal in the direction of the transmitting antenna array pattern is called as transmit beamforming. Keep in remembrance. Through this beamforming only, the multiple input single output channel is converted into a scalar additive white Gaussian noise channel, and then any code, turbo codes, convolution codes can be utilized for optimally retrieving the signals. So in both the single input multiple output and multiple input single output examples, the benefit of having multiple antennas, either transmitter or receiver, is that it has a good power gain. This is the reason for choosing. So far what we have seen is all for plot fading channels. So next we are going to see for frequency selective channels or frequency selective fading channels. So this frequency selective fading channel is characterized with coherence time, which is time invariant, where the capacity is known and it is achieved with an optimal power allocation that water fills in time over frequency. So in the time varying frequency selective fading channel, the capacity is always unknown in general. However, the channel can be approximated with a set of independent parallel flat fading channels whose capacity is the sum of capacities on each channel with power optimally allocated among the channels. So the capacity of such a channel is known, and the capacity achieving a power allocation is done through water filling scheme over both time and frequency. So what is this water filling scheme? Is that this water filling scheme is an optimal power allocation system where a water filling methodology is being used in with respect to time, as where data rate and power are increased when the channel conditions are favorable and they are decreased when channel conditions are not favorable. If this channel is giving good efficiency, then we can increase the data rate and power. And if we consider that this channel is not going to give us good efficiency, then the power and the data rate can be decreased. So depending upon this criteria, which we call it as water filling mechanism. As just we fill the water in a water bottle, if water is full, We don't pour water. If water is not there, we pour water. Okay, so this frequency selective fading is a transformation to a parallel channel where the time invariant L tap frequency selective additive white Gaussian noise channels will have an average power constraint P on each input symbols. So which is given as y of m is equal to summation L is equal to 0 to L minus 1 H L x of m minus L plus W of m. So the communication over ith channel is yn of I is equal to hn dn of I plus wn of I, where n varies from 0, 1, 2, 3 till nc minus 1. So here di is equal to d naught of I, d naught of 2 till d naught of nc minus 1 of I, the whole transpose. Similarly, w of I is equal to w naught of I, w naught of 1, w naught of 2 till w nc minus 1 of I, the whole power transpose. So this is your frequency selective fading channel block diagram. Where the information is being present here. The information bits are coded onto an encoder, and from the encoder it is being sent to an OFDM modulators, orthogonal frequency division multiplexing modulation schemes, and each OFDM symbol will lead to a corresponding channel for its usage. So each channel users use corresponding to an OFDM block. The coding can be done across different OFDM blocks as well as over different subcarriers. So this channel is considered here. The channel is considered to be as a frequency selective channel. The frequency selective fading channel will have an overhead in the cyclic prefix relative to the block length NC that can be made arbitrarily small by choosing NC as larger. NC is your chip rate. The capacity of the original frequency selective fading channel is the same as that of the transformed channel as NC tends to infinity. The transformed channel will be a collection of subchannels, one for each subcarrier n, and each of the subchannels is an additive white Gaussian noise channel. Where the power constraint on the input symbols in time translates to 1 on the data symbols on the subcarriers using the Parseval's theorem of discrete Fourier transform. It's an application of the Parseval's theorem of discrete Fourier transform is being used in this frequency selective fading channels. So the maximum rate or data rate of the reliable communication of this will become summation n is equal to 0 to nc minus 1 log of 1 plus p n of hn the whole square by n naught bits per OFDM symbol. The optimal power allocation will be depending upon the coding being obtained as Cn capacity of the transformed channel having NC to be as infinity will become maximum value of P naught till P nc minus 1 summation n is equal to 0 to nc minus 1 log of 1 plus Pn of hn squared by n naught, where summation n is equal to 0 to nc minus 1 Pn is equal to nc into P, and Pn is greater than or equal to 0 where n is equal to 0 till nc minus 1. So the coding independently varies over each of the subcarriers. You can see for each subcarrier, the architecture with appropriate power and rate allocations achieves the capacity of the frequency selective fading channel. So the coding across subcarriers cannot improve the reliable rate of communication, can still improve the error probability for a given data rate. So coding across subcarriers, across this information bit subcarrier, this 1, 2 can still be useful in practice, particularly when the block length for each subcarrier is small, in which the coding efficiency effectively increases the overall block length. So this diagram represents the information bits which are being passed on to the encoder subcarrier 1, encoder subcarrier 2, then to the OFDM modulators if required, then to the channels which are used as users. So next is the power filling, water filling power allocation method. So the objective of this function is jointly conclaved in the powers, and the optimization problem can be solved by Lagrange's method, so which you had studied in mathematics 3. Here we consider the capacity of a time invariant frequency self-defeating channel, where the capacity analysis is done as like that of a flat fading channel, but with the time axis replaced by the frequency axis. Instead of time axis, we go for frequency axis. So they are the time invariant channels which are used for water filling allocation scheme. So we get for the Lagrange function as L of lambda comma b naught till Pn c minus 1, which is equal to summation n is equal to 0 to nc minus 1, the Chiplet log of 1 plus Pn Hn the whole square by n naught minus lambda. Lambda is your Lagrange multiplier. Lambda into summation is equal to 0 nc minus 1 Pn. So the Kuhn-Tucker condition for the optimality of the power allocation is dou L divided by dou Pn, which is will be 0 if Pn is greater than 0, and it will be less than or equal to 0 if Pn is equal to 0. The power constraint is met as P equal to 1 divided by Nc, summation n is equal to 0 to Nc minus 1 by lambda minus n naught divided by Hn square. Next is the discrete Fourier transform of the DFT. H of f will be equal to L is equal to n minus 1 HL e power minus J2 by LF divided by W, the bandwidth. And the function varies from 0 to maximum bandwidth W. So the optical power allocation converges to P star of f, which is 1 divided by lambda minus n naught h of f the whole square. So this is your water filling mechanism scheme. So the power allocation can be intercepted as water filling over frequency. So if there are NC subcarriers, depending upon the chip rate, the largest reliable communication rate with independent coding would be CNC bits per OFDM symbol or CNC bits per second per hertz, as NC tending to infinity. So the capacity of this frequency alternating channel will be C is equal to 0 to integral 0 to W log of 1 plus P star of f h of f squared by n naught into df, which is bits per second. So here at the bottom is a graph with respect to the number of subcarriers and The 1 by lambda which is the Lagrangian. You can see that here the water level. You can see that this blue indicates the water level. T3 is the distance from 1 by lambda to the bottom. P2 is the distance being from here to this point, and P1 is 0. And you can see comparatively with this point, the second subcarrier is a power allocation. So these are the references. Any queries? So with this, today's presentation is over. So any queries you can type in chat box. So 5 to 10 minutes of time is given. After that, we'll have our QA session. Okay. Thank you, Navya. Yes, okay. Thank you, Lokeshwar, for your feedback. Since there are no queries, we'll proceed on to the Q&A session. Kindly be awaited. Yeah, today a question has been given in chat box. AWGN absolute white absolute white Gaussian number, additive white Gaussian noise, additive white Gaussian number. So you can type your answers in chat. Yeah, most of you had given correct answer. AWGN stands for additive white Gaussian. Credits to Shankar Narayana, Vinita Lokiti, Srivalli, Meghala, Manikanta, Navya, Chama, Atlandeshwari, Ashita, Ravi, Teja, Pradeep, Deepti, Chakri. Credits to all those who have given right answers. So today's attendance sheet is given in chat box. The link will be till 4 p.m. today. If you have any other, type in chat box.